Okay, so now we're going to introduce this idea of the adjoint of a numerical method. So the adjoint of a method. And if you will, this is motivated by the following observation or the following property of the exact flow map. So the flow of an autonomous differential equation y prime is equal to f of y, right? Y of t0 is y0, satisfies the following property. So it satisfies the property that if you take the negative time step, so you take a time step, or you take a step, it's like by negative h, and then you take the inverse of that flow map, that this is really nothing more than the flow map with a positive time step. Okay, so so that's an observation. But this is not, in general, satisfied by a one-step map. Of a numerical method. So the point is that even though it's like the exact flow map, but there's a property that taking a negative step size and then taking the inverse of that corresponding map gives you the forward time version of the map. The same is not necessarily true. It's like when you do that for some numerical one-step method. So then we're going to define for you, if you will, the adjoint of that method. It's like by looking at this construction where you take a negative time step and you take the inverse of that map. Okay, so the definition, the adjoint method which is denoted by this star, right, of a method is given by, again, taking a negative time step and then taking its inverse. Okay. So this is just defined to be the numerical one-step method with a negative time step and then the inverse of that map. Okay. So, so what does that mean? Okay, so implicitly, so let me just put this in other words, right? If you have that y1 is the adjoint, okay, of some initial condition y0, right, then this is implicitly defined by the condition that y0 is equal to the negative time flow, well, negative time, it's like one-step method applied to y1. Okay, so if you can invert this relationship, then you can tell what y1 is in terms of y0. Okay, and then we say that a method which satisfies the property that it is its own adjoint, which is to say that the adjoint of the one-step method is the method itself, right? Which is more or less, it's like the condition which holds true for the exact flow map. Okay, say this is this method is called symmetric. Okay, or self-adjoint. Okay, So both those terms are used. Okay. So let's look at a few examples, if you will. It's like of adjoints of methods. Okay. So as an example, let's look at the adjoint of the, so consider the adjoint of the Euler method. All right, so let's try to use this definition, right, which is to say that look at y0 is equal to the negative time h flow applied to y1, okay? And the Euler method, it's like applied to y1 with a negative h time step is y1 minus h f evaluated at y1. Yes? And so, of course, you can move this to the left-hand side, and this tells you that the method, the adjoint method you have, is y1 is equal to y0 plus hf evaluated at y1, which is, of course, the implicit Euler method, right? So this implies that the adjoint of the Euler method, the explicit Euler method, if you will, is the implicit Euler. Okay. All right. So you might ask, well, what are some examples of self-adjoint methods or symmetric methods? So let's look at examples of self-adjoint or symmetric methods. So the implicit midpoint, the trapezoidal rule, and the Sturmer-Villay method are all symmetric. Okay, so let's look at an example of this. Again, maybe let's consider the trapezoidal rule. So again, we do the same thing, right? Y0 is the negative time, it's like step of this one-step method, which is the trapezoidal rule applied to y1. Okay, so that's equal to y1 minus h over 2, right? F at y1 plus f at y0. Okay, and again, it's like you can reorder this to get y1 is equal to y0 plus h over 2 f of y0 plus f of y1, which is, of course, again the trapezoidal rule. So this illustrates to you this idea that the trapezoidal rule is self-adjoint. The adjoint of the trapezoidal rule is again the trapezoidal rule. And so it's sometimes referred to, as I said, as symmetric as well. Okay, so let me state a theorem now about symmetric methods. And in particular, the order of accuracy properties of symmetric or self-adjoint methods. Okay, so the theorem is the following, that let's say you have the exact flow, and then you have a one-step method. Of order P, okay, such that you can relate the one-step method with the exact flow. Well, let me just apply it to a particular initial condition. okay, plus an error term which looks like c y0 h to the p plus 1, right? So this is the leading order error term, right? The difference between the two flow maps, the exact flow map and the numerical one-step method is the truncation error or the local error, which has the form big O of h to the p plus 1 for an order p method, right? Plus higher order terms, big O of h to the p plus 2. Okay, so the claim is that if you basically, if you know the truncation error or the local error of a particular one-step method, then you can use that information to say something about the truncation error or local error of the adjoint of that method. Okay, so then the adjoint, okay, has the same order P, and furthermore, right, the adjoint method is related to the exact flow map, but where the constant or the error term looks like -1 to the p c of y0 h to the p plus 1 plus big O of h to the p plus 2. Okay, so and this is something you can check basically by definition of the adjoint, and using the fact that the exact flow map is self-adjoint, basically. Okay, so so this theorem, it's like relies again on following the definition of the local error and then using the property that the exact flow map is self-adjoint. Anyway, so let's not worry too much about the proof of this, but I think there's an important consequence of this which deserves to be emphasized. So in particular, okay, if the method is symmetric, then its maximal order is even. Okay, and you might ask, well, why is that the case? Okay, so if the method is symmetric, then the method and its adjoint are the same, so they both satisfy this kind of error relationship. And so let's think about what happens, right? So if the method is order p and p is odd, okay, hypothetically, right, then what will happen is that you have this leading order error term, but in one of the cases you have c y0 as a coefficient. In the other case you have minus c y0 as coefficient, because if p is odd, it's like -1 to the p is -1. Okay, so all right, so on the one hand this is equal to cy0 h to the p plus 1. On the other hand, it's also equal to, it's like the leading order term is also equal to -1 cy0 h to the p plus 1. And so the only possibility of that being true is that cy0 is actually 0. So basically that means that the leading order error term cannot be sort of something where p is odd, because it's like that means that that leading order error term turns out to be 0. And so it has to be that the sort of the first non-trivial error term has to be something which is has p even, because when p is even, then it's like that error term is the same, it's like in both cases, and that's perfectly consistent. Yeah, so again, what that basically tells you is that that it's, you know, it's like that the order of a symmetric method is always even. Okay, so that's an interesting observation. So why is that interesting? That's interesting because so we talked about a few of the methods we've seen before, like the trapezoidal rule, you know, it's like the midpoint rule, it's like implicit midpoint rule, and the Sturmer-Villay method as being symmetric. Okay, so and as you might recall, they're also second order accurate methods. So this theorem, if you will, is like gives you an alternative way of proving that they're second order accurate. So if you're willing instead to prove that they are symmetric, then proving that they're symmetric together with proving that they're at least first order accurate allows you to then leverage this theorem to say that it's second order accurate at least, right? Because if it's at least first order accurate, but it has to be even, right, then that means that the order of accuracy is at least 2. Okay, and it could be higher, but it's like, again, this argument sort of allows you, if you will, to save that one last step in the error analysis. If you've already proved that the order of the method is odd, you're then guaranteed that you get one higher order just by virtue of the fact that the order of the symmetric method is actually even.